Earthquakes occur at faults or fractures in the Earth's crust, where two big slabs of rock meet. Movement under the surface tries to push the rocks past each other, but the rough edges get stuck together until enough stress builds up to jerk them past each other. And this violent jerking can cause devastating quakes. But a new instrument, and an experiment being carried out in France, has shown that we might actually be able to relieve this stress using a technique called fluid injection, as Jean-Philippe Avouac explained to Heather Douglas.
So this instrument is a quite new instrument which allows to measure the displacement across a fault. There are several fiber optics which are anchored to both sides on the fault, and we measure the stretching of those fibers during the displacement on the fault.
This instrument is put into the bedrock. Is that what we've got in front of us?
You have in front of us an example of an exhumed fault.
It's quite a big chunk of rock, and you can see that there's rough bits, and then there's a smooth bit with lines, and that's a bit green and smooth.
Yeah, so what you see here is the fault plane with these striations which indicate that some frictional sliding has occurred. And the green stuff is due to minerals that were deposited because of fluid infiltrating along the fault. So it shows that on natural fault like this one, you have some interplay between faulting and fluid circulation. And we wanted with this experiment to understand a little better how this interplay is working and the influence on the behavior of a fault.
And you did that by actually injecting fluid into a fault and seeing how it reacted?
Exactly. So for this experiment, we've had access to an underground facility in southern France. We've had access to a tunnel at a depth of about 900 feet. And this tunnel is close to an old fault, which is relatively large, but which is not active at the moment. The point of the experiment was to drill into the fault and then pump in water and to see how the fault would respond.
What's the real benefit of injecting water and then seeing how the plates react?
We developed a dynamic model of earthquakes, but when we do these numerical simulations, we need to put in some realistic mechanical properties. This experiment provided direct observations that we can then use to determine the friction law, how much stress you need to put on the fault to initiate sliding. We can then put them in the numerical simulations that we can use to estimate how an earthquake nucleates, and once it has nucleated, the probability that it can grow big or not.
By using this new instrument to measure those properties, you can evaluate a fault and see how likely it is for an earthquake to happen.
Exactly. So once we have these measurements, we can in principle determine whether the fault is prone to produce seismic ruptures or would rather slide. The thing is that once we inject water, we might change the properties at the same time. So for example, what we observe with this fault is that it is mostly sliding without producing earthquakes. So it is not completely clear at this point if it's directly the effect of the water which is promoting creep, or whether it's an intrinsic property of the fault zone. We are working on that. I tend to think that in fact it's because we are injecting the water that we promote creep.
You're saying that by injecting this water, you can change the stress properties, and perhaps you could change a fault that's prone to earthquakes and sticking so that it's got less friction and therefore it creeps instead, and that's the faults that we like.
Yeah, exactly. So that's the exciting part, that you could think of relieving the elastic stress, which in principle could produce large earthquakes in the future, by injecting water in the fault and relieving the stress by very slow creep. At this point, I don't recommend trying to do that on an active fault because you would relieve the stress at the point where you're injecting water, but the stress would then increase around it and you would produce earthquake on the edges, just like we did in this experiment. What we can do instead is constrain the mechanical properties and then do numerical simulations to evaluate how an active fault would respond to such an injection and start to think about maybe engineering faults in the future.
The University of Cambridge's Jean-Philippe Avouac, and his work was published in the journal Science this week.